All right.
Okay. One, two, and three. Hello, how's it going? My name is Tyler Valderrama, and the other I have,
Michael, okay, Bakuro.
and we will be presenting quantum computing, a new kind of computing. Now, what is quantum mechanics? Quantum mechanics is basically a quantum computing that uses rules of quantum physics instead of classical physics. Classical computers use bits. Each bit is either 0 or 1. Quantum computers use qubits, which can be 0 and 1 at the same time. This allows quantum computers to explore many possibilities at once.
And this topic matters most because of its applications in regards to AI, big data, and cybersecurity, which could play a big role in the future and are already a part of many modern jobs and our current digital infrastructure. And quantum computing could affect these, particularly by changing how you protect data, improving some data as some AI and data science tasks, and improving techniques for solving large complex problems in math and science. And knowing the basics can help us prepare for a quantum informed future as well.
Okay, now classical computers and their limits. The classical computers use bits 0 or 1 and logic steps to process information. It can also power the internet, apps, video games, and data centers, whereas their limits can cause some problems that are too large and complex. Some of the examples is factoring huge numbers and simulating big molecules. Now, for these problems, the time needed can grow faster than computers can handle.
And this all started with Feynman's idea, leading to the birth of quantum computing. In the 1980s, physicist Richard Feynman suggested a new approach. That is, to study quantum systems using a quantum machine rather than a classical one. Classical computers, after all, need too much memory and time to track all the quantum states. So instead of fight quantum effects, we sought to use them instead for such purposes.
And as for qubits and superposition, for starters, qubit is a quantum bit, main building block of a quantum computer. Superposition is a qubit, can be in a mix of 0 and 1 at the same time. Nielsen and Chuang, 2010. That's the reference right there. Example is like a spinning coin that is not just heads or tails while in the air. When we measure a qubit, it becomes 0 or 1, but before that, it behaves as both.
Many qubits at once. Within classical bits, systems holds ones of 2 to the n patterns at the same time. With n qubits, though, systems can be a superposition of all 2 to the n positions at once. We still only get one result when we measure, though. Quantum algorithms use interference so that the correct answers are more likely and the wrong answers are less likely.
Now, as far as for entanglement is a strong quantum link between qubits. Now, deciding through that, we measuring one entangled qubit tells us something about the other, even far away, from Nielsen and Chuang, 2010. It lets qubits store complex relationships between pieces of information. It is helpful for optimization problems with many linked choices and simulating systems where many parts interact.
And quantum computers also utilize quantum gates, similar to AND, ORs, and NOT gates in classical computers. Gates can change the state of qubits, so gates flip 0 to 1, and some gates create superposition. Two qubit gates, like CNOT, can create entanglements, though. Putting many gates together forms a quantum circuit, which can then implement a quantum algorithm.
Now, the key algorithms is Shor and Grover. Now I differentiated both of them. Shor's algorithm is it can factors large numbers much faster than known classical methods. This is a threat to RSA and other public key systems. Montanaro 2016. As compared to Grover's algorithm, it speeds up searching in the unsorted list. Classical, about n steps. Quantum, about square root n steps. And I found that from Montanaro 2016. It's important for brute force attacks, so keys may need to be longer.
Different physical systems use qubits as well, such as the superconducting qubits utilized by Google and IBM, trapped ions controlled by lasers, and photons, light-based systems, according to Young Soy and Emery from 2019. In 2019, Google's Sycamore, which has 53 qubits, completed a special task in 200 seconds. Claims quantum supremacy over classical supercomputers.
Now, the NISQ era and who is involved, we are in the NISQ era, noisy intermediate scale quantum. The devices has tens to hundreds of qubits. They are noisy and not fully error corrected. Major players that are in this era are either big tech, such as Google, IBM, Microsoft, startups, Rigetti, D-Wave, and also universities and government programs such as National Quantum Initiative. Some quantum devices are available through the cloud.
And here are the impacts that quantum computing could have on cybersecurity. So, as we all know, many current cybersecurity systems rely on factoring large numbers and discrete logarithms, specifically large prime numbers. And the large stable quantum computers, on the other hand, running Shor's algorithm could break this, which could, of course, imply breaking online banking encryption, meaning that you could have more data breaches for banks. And of course, secure websites and digital signatures, according to Montanaro 2016. In the long term, attackers could save encrypted data now and just break it later as well. Hence why even with post-quantum encryption algorithms, quantum computing could still pose a threat.
Now, for post-quantum security and quantum key distribution, the response is develop post-quantum/quantum safe cryptography. The new scheme is designed to stay secure even with quantum computers. The quantum physics can also improve security, which is the quantum key distribution, KQD. It uses qubits to share keys, and eavesdropping can be detected. Cybersecurity students need to learn about both, about the quantum threats and quantum-based protections.
Many AI and many tasks in AI and big data involve searching large spaces, optimizing parameters, and heavy math in large data sets. Quantum algorithms could speed this up by solving systems of equations and other data analysis tasks as well. Hybrid and variational quantum machine learning is also on the table as well, with quantum circuit as a model adjusted by a classical computer, which of course are designed by NISQ devices, according to Montanaro 2016 and Freescale 2018.
Okay. Then as for optimization and simulation, many real-world problems are optimization problems, such as delivery routes, resource management, and investment choices. Quantum and quantum-inspired methods aim to search through huge solution spaces more efficiently. The quantum simulations is either simulating atoms, molecules, and materials. It's hard for classical computers. Quantum computers naturally handle quantum states. It could help design new drugs, materials, and clean energy processes.
Some technical challenges to consider. Such include decoherence. As qubits lose their quantum behavior due to noise from the environment. Noises and errors in gates make results unreliable. Quantum error correction as well uses many physical qubits to store one logical qubit and runs checks and fixes without destroying the quantum states. Huge scales required. Breaking Strzok encryption might need millions of qubits. Today's devices are still small and noisy.
Now, scaling up and engineering issues. It could be controlling thousands of millions qubits is very difficult. Superconducting systems, which requires more qubits, which means more wiring interference. Trapped ions need complex traps and moving ions with low error. Photonics need chips with many optical elements and low loss, and the progress needed in materials, chip designs, control electronics, software, and automation.
Some social ethical questions also need to be considered. Such an example would be security, which needs to be improved on through quantum safe encryption before large scale quantum computers could exist and wreck, all the encryption that exists today. And of course, there's also questions of who has control over the powerful quantum computers, and and if it be the government, like what's responsibility would it have as well, or the corporations as well. Risk of wider gaps between rich and poor countries and companies are also of concern here as well. As for the potential benefits that could be involved, there is hope for new medicine, better batteries, and a cleaner chemistry, which could be achieved via quantum computing. And to reach these goals fully, we'll most likely need better education, international cooperation as well, and clear rules and guidelines on what can or can't be done or who can own a quantum computer.
Now, the future is hybrid systems. Now, experts expect hybrid systems, not fully replacement of classical computers. Quantum processors act as special helpers for certain tasks. Classical computers still handle data storage and general purpose computing. Now, in today's world, small quantum devices are already available through the cloud. As qubits counts grow and errors drop, more real-world applications may appear.
Conclusion: quantum computing is based in qubits, superposition, and entanglement. It may give big speed ups for searching, factoring, optimization, and quantum simulations. The field has also grown considerably from theory to real hardware by major companies and labs, and we're currently in the NISQ era. Noisy devices, but useful for learning and experiments, which could help for better development of quantum computing once we get the better materials. And for students in CS, data science, cybersecurity, quantum computing is of benefit and interest because it's a growing and emerging field, not just science fiction. And learning the basics now prepares us for a world where classical computers and quantum computers work side by side. Here
And last but not least, here is our references, and I hope you enjoyed the presentation, Professor. Thank you for your time.